Before I get started, can you confirm again? Can somebody confirm again if you are hearing me clearly? Is everyone hearing me clearly? Can somebody confirm if you are hearing me clearly? By talking. I also want to, okay, thank you so much. I also want to make sure I'm hearing you as well. Can somebody confirm by talking if you are hearing me clearly?
Yes.
Yes, yes.
Thank you. Thank you so much. Okay, so I want to welcome you to my lecture today. And of course, today we got two materials to work on. The first one is data and covariance matrix. So, in the outline, I'm actually gonna walk us through the data matrix, the covariance matrix, and correlation matrix. Of course, on Monday. Uh, we're gonna finish this outline. Monday the focus will be on miscellaneous topics. So on the data matrix, I'm gonna walk you through the definition, the properties, and not only that, I'm gonna show us you some articles. Of course, um, you need to be able to get yourself familiar with the articles because whenever assignment is given, we expect you to use our software. Okay, so let's get started. I'm going to start, like I said, uh, with data matrix. I remember in my first class, I actually, you know, told you that we live in a world where we actually we want to understand our environment. We want to understand our political environment. We want to understand a medical environment, economic environment, and so on like that. So, for us to have that understanding, we need knowledge. And where will the knowledge come from? The knowledge is going to come from information we got. And where will the information come from? Information is actually going to come from data, okay? And when you collect your data, okay, information that we need, okay, the information that will translate into our knowledge is not readily available. Of course, the data need to be analyzed. Data need to be analyzed using what I call using appropriate statistical methodology. So, what I want to showcase right now is actually the starting point, okay, for almost all multivariate analysis, okay, which is having the data. Now, the data that we want to talk about, when data are collected, of course, they actually going to be in form of a matrix. They are expected to be arranged in row and columns. You can get your data actually um you know uh in rows, maybe based on observations that you have, or based on the observation could be subject, it could be countries, it could be cases, it could be even be time in case you are working with a time series data. And of course, you collect that over so many variables. So we expect the variables, to occupy the column and the observations to occupy row. Okay, so that's what I mean. So the this is going to take a look. You should take a look at what I'm actually displaying right now. Okay, we actually going to use matrix. Okay, the data. That's why it's called data matrix. Because we're having our raw data arranged in matrix form, as you can see. So here, if you take a look at the hex here. I'm assuming the hex here is of n by p dimension. N by p dimension in the sense that n represent, okay, the number of observations, and of course p represent the numbers of variables. Okay, and that's exactly what you're seeing here. Okay, so I just want you to understand this, that before this particular data set, they actually contain the original measurement. Okay, and of course, they actually gonna have units. Imagine you collect data from 100 individuals over, you collect data on their height, weight, and ages. Because I have height, I have, give me 1 second, I'm gonna write this. Okay, so I'm giving you an example right now. Okay, so maybe you have data on height, okay, based on height, based on weight, okay, and age. Okay, so in that case, you got three variables. So in a situation where you have three variables and you collected that over 100 observations, I'm actually going to call that 100 by 3. Okay, that's what I mean by N by P. Okay, so N represent the number of observations and P represent the numbers of variables. That's exactly what I mean. Okay, so I'm actually presenting to you the data matrix. So this is what we call data matrix. Okay, so any data matrix, we can actually extract a collection of column vectors. Okay, so which is what I'm actually displaying right now. Okay, we believe that the column, we talk about the column vectors, we are talking about a particular variable. It could be height, it could be weight, it could be age, and so on like that. So when you say 1 to P, so what I'm actually talking about here is that I have P numbers of variables. That's exactly what I mean. And of course, so if you take a look at this now, so this is like n by 1. Okay, this is by n by 1. So we talk about the Sj here, give the jth variable score for n items. Okay, so if I have n items, I'm actually interested in what their variable the variable score is. Okay, so we also have a collection of row vectors. Okay, we talk about row vectors. Take a look at this guy now. The dimension here is 1 by p. Okay, so the 1 by p, the vector x here actually talking about the item score for the p variables. So we just wanted to understand that. So what we're doing right now, we just trying to look into the matrix algebra form of our data because multivariate data always in a matrix form, and of course you need to be able to understand, get yourself familiar with which one represent the columns and which one represent the rows, and of course what do they depict in real life. Okay, now let me tell you this. When I have data set, like for instance, if I come back here, okay, if I actually come back here, okay, this is massive in nature. This is original data set, the original measurement, the raw data set that are also in unit that have not been processed. Okay, this has not been analyzed, this has not been processed, but uh, as part of the preliminary investigation here, if I want to, I can begin to summarize the data here. If I want to summarize the data, I can decide to find the mean. I may want to know the mean of each variable. I remember the other time, I set an example. If I collect, data on maybe I want to look into the consideration, what is the height, the weight, and the age of students in my class, and maybe what I'm interested in. I want to know what does it mean of the age? What does it mean of the height of all students in my class? Or what does it mean of you know any other variable that I may be interested in? So this is the formula. That's what I mean. Okay, if you take a look at what I have here now. So this is the formula, okay? So this is when I'm actually interested in figuring out the mean of each random variable of each variable. And you know what? If I want to find the mean, it means I'm actually going to consider all the observation, okay, in a particular column. I want to find the mean of each column. That's exactly what I mean, okay, here. Okay, and that's what I call, calculating the variable means, the column means, okay, which means I'm actually interested in the mean of each variable in the data set. That's what I mean. Okay, so do you know I may also be interested in the mean of or observation? Okay, so which means if I want to get the mean, maybe for instance, you know, my data is on age, weight, and height of my student, and maybe what I'm interested in, I actually want to figure out what is the mean of that particular student. When I want to talk about the mean associated with a particular student, then it means I'm going to sum the values across the variable or the variables for that particular student. And that is exactly what you're seeing here. Why we're doing summation that divided by P. Because here, the mean that we're interested in is the mean of the height item. The height item may be a particular student, may be a particular observation. That is exactly what I mean. And this is how to get the mean in a scalar form, and this is how to get a matrix form. Okay, just wanted to take note. Okay, before I move into example, is there any question? Is there any question before moving to example? Is there any question? Okay, so silence implies you understand this. So I'm actually gonna move into example now. Now, I want to show you example of data set, multivariate data set. This particular data set is in R, and if you want to have access to that, of course, if you put this into your R interface, you're actually gonna have uh, you know, access to the data. Well, yeah, what I just want to show you the first six observations in the data set. So take a look at this guy here. Okay, if you take a look at that, that is the data frame. Okay, so these are the observations that I talked about the other time. These are the observations. Okay, these are the observations. So right now, I'm showing you for the first six observations. And you know what? This guy here are the variables. Okay, you need to take a look at that. So we have observations in the row and the variables in the columns. Okay, I just wanted to take note of that. So if you take a look at this, this is the data frame, and of course, this actually is in matrix form. If you take a look at what I have. Okay, so when you take a look at this right now. If I actually want to convert this into matrix form, because the way it is right now, this is a data frame. This is the original data frame. Okay, this is like the data that you collected that you store in your Excel file, okay, in your spreadsheets, okay. And you know what we want to do right now? The very first thing that we're gonna do in multivariate analysis is can we have a way to put this data frame, data set, in a matrix form? I'm gonna say that again. Well, we already have our data set, maybe probably store in a spreadsheet. And what we want to do right now for the purpose of analysis, because the techniques that we applied in multivariate analysis are actually going to work when we have our data set in matrix form. And can we have a way to generate a code in R, okay, so that we can have this data frame in matrix form? And of course, the good news is we can actually do that. So take a look at this guy. This is the code right now. Okay, so actually gonna say X. Okay, can you see that AS dot matrix empty cows? Because the name of the data set is actually empty cows. Okay, if I want to know the dimension, if I really want to know how many observations do I have and how many variables do we have, so in R, I can actually I can do this. That is DIM. If you take a look at the DIM, okay, the DIM, it means dimension. Okay, so here we have 32 by 11. 32 by 11 means we got 32 observations. It gives 11 variables. That is what that means. So I'm not sure, like I said, I'm not showing you all the observation here. I'm only showing you the four C's. They are more than that. You can see here, this is saying we have 32 observations. Okay, so that is a code now. Just want you to see. Okay, that is a code now. Okay, so if I have that, the next thing that I'm actually gonna do, you remember the other time I was talking about getting the variable means, the column means, the row means, here, how do we actually do that in R? Okay, how do we do that in R? So this is how now I need you to pay attention. Okay, in case you're not getting, in case you get stuck, in case you need clarification, please let me know. Now, let me tell you this. What do I want to do right now? I actually want to find the column means and the row means from my data set. Okay. And let me tell you this. If you want to do this in R, we have several ways. There are different kind of ways that can be implemented in R. Okay, we have easy ways to do it. We have hard ways to do it. But I'm actually going to show you. Take a look at this. I actually want to find the color mean. Give me 1 second. Okay, so take a look at this guy now. Okay, so the, I want to start by finding the row means. Okay, if I want to find the row means, okay, it means I'm actually interested in finding the means of the items, the means of the observation. But you know what? I showed you the other time, we got 32 observations, but maybe we are only interested in the first three observation, and that is what this guy mean. It means I'm not interested in finding the mean of all the observations. I'm only interested in finding the first three rows. That's why you see 1 to 3. If you are interested in finding the means of all the observation, all we're just going to do is just 1 to 32. Don't forget, we got 32 observations in all. But for simplicity, I just want to show you, when you are interested in finding the mean of the first three rows. Now, as you can see, you're just going to write the row means into X. Don't forget, we've already defined S as our matrix. Okay, and we're trying to tell you how here that, okay, you know what? We only want to focus on the first three rows. Now take a look at what we got. So the first three row, the means for the Mazda, the means for this, the means for that. Take a look at that. Okay. So and another way to do that. So this is the first way. Okay. I just want you to pay attention now. Okay. So this guy, this is one way to do it. The one way to do it is actually going to give you these results. Okay. That's one way to do it. Another way to do it is this. It's still going to have the same results. Okay. And another way to do it is that. Can you see that? I just show you three different ways, to implement that. And that will give us the same results, as you can see right now. Now, I've done this for row means. I can also do the same for column means. Okay. So don't forget, for column means, I can find the means of all the variables in my data set, but I choose here to just, I'm interested in the first three columns. The first three column is MPG, cylinder and DISP. Okay. And of course, here I'm also showing you the three different ways of implementing that in R. Before I move to the next slide, is there anyone who actually want to ask a question based on this slide? Is there anyone? Uh, I want to confirm again. Can somebody confirm again if you are still hearing me clearly? Is everyone still hearing me?
Yeah.
Thank you so much. And thank for confirming that. Now, actually moving now, I want to move to the next slide. Now, I needed to pay attention. Uh, what we just found here. We found the mean. Don't forget, uh, one of the measure of sexual tendency or measures of location. One of them is the mean. Don't forget, we also have median, we also have mode. So the same way we find the mean, we can also do the same to the median. So right now, here on this page, I'm only trying to show you how to find the median. Okay, you want to find the median for the first three variables. You also want to find, uh, you may also want to find the range. In statistical analysis, we got different measures that we may be interested in. We may be interested in the measures of average, or that we also call measures of central tendency or measures of location, which is we could be interested in the mean, in the median, and mode, and not only that, we may also be interested in the measures of variation that we call range. Okay, so you take a look at this guy. The range is a measure of variation. We use range when data set are normally distributed. If you want to figure out how spread out, okay, you want to measure the amount of spread out in the data. Okay, don't forget the range is the difference between the highest and the lowest. So if I want to find the range for the first three variables, okay, that's exactly what I'm actually, what I'm doing now. Okay, I'm going to find the range for the first three variables and for the first two observations, as you can see. So if I have observation number one, okay, I want to find what is the range, okay, for that, what is that, what is that. So now there's something I need you to see. If you take a look at here, I'm talking about column, okay? I want to get the column ranges. And I'm focusing on three variables. The first variables are, in the MPG. Okay, the first variable is the MPG. What is the minimum? What is the maximum value of the MPG? So what I'm going to do is to find the difference between the maximum and the minimum on the MPG. Okay, so and I have that result. I can do the same thing to CYL. I can do the same thing to that. That's what I'm doing. Okay, now that's all. Now, what have we done so far? What we've done so far, I've introduced data matrix, and after introducing data matrix, I think I also walk you through how you can actually present your how you can convert your data frame, the original data in a spreadsheet, okay, into matrix form. And of course, you know why we need it in matrix form. We need it in matrix form because the approach of multivariate analysis require that we should have our data set in matrix form. Because when it is in matrix form, it should be very easy to figure out. So, and I remember I walk you through how to get some basic statistical summary, like how do we get the means, how do we get the median, and how do we actually get the range. Okay, so I want to move to covariance matrix now. But before moving to covariance matrix, is there any question at this time for data matrix? Is there any question? Okay, so if there's no question, I'm actually gonna move into the covariance matrix. okay? And I need you to pay attention. Now, I remember the other time, okay, that the very first, as part of the preliminary step in any research involving data is to collect our data, and particularly in multivariate analysis, we actually need to convert our data into data matrix, which we've already done that. And I actually show you how you can get, depending on your interest, depending on your intention, I walk you through how to find the mean, how to find the median, and how to also find the range and so on like that. So, but right now, beyond basic statistical measure, uh, because we got variables, we got some variables. Can we have a measure? Can we have a measure of how they varies together? We want to have a measures of how, they actually varies together, which is enable us to investigate if there is any relationship among the variables. Now, what we need is to talk about the covariance matrix. I want to welcome you into a covariance matrix. But before I'm going to talk about the covariance matrix, well, what is covariance itself? This I need you to pay attention. Uh, Before we can get our covariance, we need our data. Okay, right now we already have our data matrix, and of course, we can actually derive uh, covariance matrix from data matrix. So I'm actually going to say because of that, um, this is a summary matrix. Okay, it's a summary. Okay, I'm going to say I'm going to write that. Okay, it's a summary. Okay, it's a summary. Okay, this summary matrix, because it is actually, we want to summarize our raw data. Okay, and of course our intention here in the covariance is we actually want to see the way the variables move together. Do they move together or do they move apart? Okay, in general, we want to see how they vary together. For instance, if I'm talking about, if a criminologist is actually working on time variables, we actually want to see whether violence or crime is associated or is related or varies together with property crime. Okay, we may want to investigate the movement of variables. Okay, if we want to investigate the movement of variables, we actually need the covariance. Okay, the covariance will tell us the how variables move together. So right now, uh, you know, the covariance matrix is always going to be a square matrix. Okay, please pay attention. Okay, it's gonna be a square matrix, always gonna be a square matrix. Okay, and of course we use this notation to represent covariance matrix. Okay, the other time what we used to represent a data matrix was X, but right now we're using this notation now to represent covariance matrix. Now let me tell you this: in a covariance matrix, the diagonal of the covariance matrix is variances. I'm going to say that again. The diagonal of the covariance matrix, we call them variances. Okay, for instance, this guy is talking about variation within the variable, the first variable. This is variation within the second variable, the variation within the third, and so on like that. So in the diagonal of the covariance matrix, we have variances. And in the half diagonal, okay, when I talk about half diagonal, please pay attention. When I talk about the half diagonal, I'm talking about here. Oh, give me 1 second. Talking about that. Talking about that. That is what we call the half diagonal. So the half diagonal represent the covariance. So which means in a covariance matrix, we have the combination of the variances and the covariances. Okay, so when I talk about the variances, that is variation within. When I talk about the covariance, that is variation between. There's a difference between the, variation within and variation between. And how do we get each of the elements in the covariance matrix, for instance, if I actually want to get, the variation within that I call the elements in the diagonal of the variant of the covariance matrix, I'm actually going to use this. Of course, that is the formula. Okay, and if I want to find the elements in the off diagonal matrix here, okay, I'm actually going to use this guy. Okay, so I'm just trying to present that to you. Okay, now, uh, how do we actually, now, you know what I want to show you right now? How do we actually obtain, for instance, how do we derive covariance
Excuse me,
matrix?
Professor.
Okay, go ahead. Go ahead.
Yeah, so I just wanted to ask you about this. Variance within and between. What's that concept? I couldn't get it. Could you
Okay,
please briefly summarize that once again?
okay, okay.
Yeah.
That's a very good question. Let's say for instance, like what your question is, you want me to summarize, like re-explain, the covariance matrix, the one within and the one. Now, this is what happened. Let's say for instance, if I'm talking about weight, I have variable weight, I have variable height, and I have age. Okay, if I'm considering three variables, maybe I collect these three variables over my, across observation. Then let's use our class. Maybe I collect the data from every student in my class about their weight, height, and age. So when you take a look at the diagonal, okay, so when I look at the weight of students, okay, they are not going to be the same. There's a variation within the weight of student because different student will have different weights. Okay, so that is what I mean by variation within. Okay, different student we have different heights, different student we have different ages. Does that make sense? Do you understand the variation within now? That's what we call variances. Okay, so that is the variation that occur within a particular variable under, investigation. That is exactly what I mean. And if I want to get that variation, okay, if I want to figure out that variance, you know what is going to happen? Using this particular formula now, then it means I need to for find the mean. I need a mean of that variable. What is the mean height in my class? Then I will be subtracting the original, the raw, the everybody's values of the height from the mean height. I'm going to square that. When I square that, and I'm actually going to divide by the number of students in my class. When I do that, then I have the variance for that particular variable. Okay, that's exactly what I mean. So variation that occur within a particular variable, that is what we call the variances that you have in the diagonal of the covariance matrix. But in the half diagonal, for example, if I'm talking about this guy, okay, maybe I want to talk about what is the variation that we have that occur between height and weight. Okay, that is no longer called a within variation. That is called between variation because two different variables are involved. And that's why we're going to make use of this formula here for the covariance. The person that has the question, I believe, do you understand now?
Yeah. Thank you, Professor.
You're welcome. Okay, now, away from that, how do we actually how do we derive covariance matrix from data matrix? Because everything is going to start from data matrix. How do we actually achieve that? Please, I need you to pay attention. I'm actually going to go back to the data matrix. Uh, the data matrix, we actually use X. Okay, pay attention to that. This is X, right? That's a data matrix. If I have that data matrix, how do we derive the covariance matrix from the data matrix using a matrix approach? we actually want to use a matrix algebra approach. So how do we actually do that? That's what I want to walk you through right now. Now, I need you to pay attention to that. Now, look at that. If you see this guy, okay, that is the original data matrix that we have. Okay. I mean, sorry, X was the original data matrix that we have. Okay. But SC, okay, is when we center the X matrix. If you take a look at it, this is my SC. You know what I'm going to be doing? Okay. I'm actually going to be subtracting the means from each of the observation. This is what happened. Let me explain that so that you're going to understand what I mean. Take a look at this guy. You know what I've done? In the first column, I was subtracting the mean of the column. I was trying to subtract the mean of the column from each and every observation in that column. That's what I'm doing. I'm going to go to the second column. In this second column in my data S, okay, initially I have a data S, right? In the second column in my data S, I'm actually going to be subtracting the mean of that particular column from that. Maybe the first one may be age, the second one may be height, and so on like that. So what I'm just trying to do over the number of students in my class, what I'm trying to do right now, I'm actually subtracting the mean of the age from each and every value of age of student in my class. In this second column, I'm subtracting the mean of the height. Okay, the mean height is S bar 2. And I'm assuming I'm actually subtracting that from each and every raw value of height of my student in my class. Now we continue to do that until I get to the last variable. This is what we call centered matrix. Please pay attention, okay? Because this is what happened initially. We have a matrix X, okay? This is a matrix X. If I want to derive covariance matrix from matrix S, I will need to first get a centered matrix S. Now, this is a centered matrix S, okay? So what you see right now, this guy here, SC, is a centered matrix S. And the moment I have a centered matrix S, and then I found the transpose. Okay, this guy here, that is a transpose. The transpose of a matrix is when you convert the row to column or you change the column to row. Then what I'm going to do now, I'm now going to multiply the transpose of the centered matrix by the original centered matrix. And when I do that, I will divide by n, and that will give me the covariance matrix. And that is how to get the covariance matrix. So we are getting the covariance matrix from the data matrix, but the very first thing we need to do, we need to first obtain the centered matrix, and after getting the centered matrix, then we're actually going to, we're going to get the transpose of when I say transpose, okay, I'm going to write that. This is what I mean, transpose. Okay, the transpose of SC is what I call this guy here. Okay, then I'm now going to do a matrix multiplication between the transpose of the centered matrix and the centered matrix. Then I'm going to divide by n, and that will automatically give me the covariance matrix. Okay, now when I get a covariance matrix, okay, now if I want to get that if I actually, in matrix form, okay, please pay attention. That's exactly what I've done. Okay, now we have so the moment you do that, then you're actually going to get this guy how that's going to give you this. So when you do this, okay, all of that, then you're going to have that. So which is what we call the covariance matrix. In multivariate analysis, covariance matrix is very, very essential. We use covariance matrix in principal component analysis, in factor analysis, in graphical lasso, and so on like that. Okay, and that's why the covariance that we know is very, very essential. And the covariance matrix can actually be derived from the data matrix. Okay, now we want to talk about the properties because you know why? In covariance matrix, like I said the other time, the diagonal is variances and the half diagonal is covariances. So we now want to talk about the properties of the variances. Now, the variances can never be negative. I just want you to take note of that. Why is it that they can never be negative? I need you to pay attention to that. Look at that. Because it's sum squared. Okay? It's always going to be positive. It's not going to be negative. Okay? And that's exactly what we mean here. Okay? This guy actually mean for every, j variable, the variance has to be either greater or equal to zero. That should be non-negative. Let me see if somebody has a question in the chat. Okay. Okay, so let me know in case you want to ask question. Now, what I'm trying to showcase here is that the variance can be zero or greater than zero. Okay, but you know what? We want situation at where the variance will be strictly zero greater than zero. Okay, and it's gonna be of greater than zero as long as that does not exist or alpha such that we have that. And of course, the trace S, the trace S has to be greater or equal to zero. What is the trace of a covariance matrix? Is when you are trying to add all the elements in the diagonal. That's what we call the trace. And you know what? In principal component analysis, where we're going to be talking about eigenvalues, the eigenvalues of the covariance matrix are actually the variances that we call the lambda 1, lambda 2, up to lambda p. And of course, the sum of that also have to be strictly, greater or equal to zero. Now, let me tell you this. Depending on whether you have if you compare the size of your data, for instance, if you take a look at this, when the number of observation is less than P, that is, when the number of, let's say, for instance, if the number of students in my class is less than the numbers of variables, okay, there's possibility that one of the variances could be zero. When I say variances could be zero, okay, the element in the diagonal matrix of the variance covariance matrix that we call the variance could actually be zero, okay, if the number of observation is less than the numbers of variables. But let me tell you this, in a situation where the number of observation is greater or equal to the numbers of variables, of course, we are guaranteed that all the elements in the diagonal will be greater than zero. When I say elements in the diagonal of the covariance matrix, I mean the variances. Okay, and when they are zero, we actually, or what I mean is that the P column of S are linearly independent. Okay, linearly independent actually means that none of the elements in the variance covariance will actually be zero. They're all going to be greater than zero. Okay, now uh I just wanted to take a look at this. We from the Cauchy squash inequality. Okay, we actually want to have a manipulation. We want to play around variances and the covariances. Okay, Cauchy squash inequality was able to establish the fact that the square of the covariance, whenever you see SJK, it means I'm talking about variation between variable J and variable K. Okay, it's like I'm having Sj and Sk. So the square of that is less or equal to the product of the variance within. So what I'm trying to talk about, for instance, if I'm talking about height and weight, okay, now this guy is trying to say the square of the covariance between height and weight is less or equal to the product of the variance of height and the variance of weight. Okay, so and this is only going to hold if we realize that the two variables are linearly dependent. Okay, they are linearly dependent. Okay, and of course, if you take a look at this, when I take the square roots of both sides, I'm actually going to have this. Okay. And when I take the square root of variances, each of these will now be called standard deviation. Okay. Now let me tell you this, in case you care to know, there's a difference between variance and standard deviation. Okay. They start the variance and standard deviation, even though they actually measures of variation, but variance is in a square unit, while standard deviation is not in a square unit. The standard deviation has the same unit as the units of the mean, but the variance does not have the same unit as the unit of the mean. So I just wanted to take note of that. Now, how do you get covariance matrix by hand? Okay, like for instance, you want to code this in R. Okay, I'm actually going to show you the hard way to do that. We also have easy way to do that in R. Okay, so if I need to define the number of observation, which is the numbers of row of S, then I need to specify. So this is like writing a formula how. This is a hard way to do it. So right now, you know what I have? This is now giving me the covariance matrix. So this is a covariance matrix. Here I'm only specifying that I need for three of so for six variables, so 3 by 6. Okay, if you take a look at what I have here. Okay, this is another way to do that now. This is when I'm actually coding the centered matrix, the transpose of the centered matrix multiplied by central matrix divided by that. But this is the hard way to do it in R. But we have easy way. Okay, we have easy way. The easy way to do that in R is this. Since I actually define S to be my matrix, if I want to get the covariance in R, I'm just going to have a COV. Oh my God, with the COV of that, I'm actually going to have the covariance. Okay, that I want to the covariance matrix. And of course, if I want to look into the dimension of the covariance matrix, of course, it's like I said, it's a square matrix. So it's going to be 11 by 11. If you take a look at that. Okay, so now what is next? I think where I'm actually going to start from on Monday, I'm going to start from correlation matrix because there's a difference between correlation matrix and the covariance matrix. But let me first tell you before I go, what is the difference between covariance and correlation? The covariance will only tell us how variable varies together, but we cannot use covariance. Covariance cannot tell us the strength of the relationship. And why is it that we cannot use covariance, to measure the strength of the relationship? Because the covariance depends on the unit of variables. Okay. For instance, if you are working with centimeter and you now change that to kilometer, the covariance is going to change. The covariance is not consistent. Okay, and that is why we cannot use covariance as a measure of the strength of the relationship. So the covariance can only tell us about how variable varies together and whether they are positively related or negatively related. It can tell us that, but it cannot tell us what is the strength. Okay, is it weak? Is the relationship weak? Is the relationship strong? It cannot tell us that. And that is why we need a correlation matrix. Okay, the correlation is we're actually going to do something to covariance to get correlation, okay, by standardizing. When we standardize covariance, we're actually going to have a correlation because the standardization actually we actually make it unitless. It's not going to have units. When you change from a unit to from one unit to the other, okay, the correlation value is still going to be consistent. So I'm actually going to start from correlation matrix on Monday. We're actually going to return to in-person teaching on Monday. Is there any question before I go today? Is there any question? Is there any question before I go today? Okay, I want to appreciate every one of you for attending my lecture today. And I also want to say I've already published the last lecture on my YouTube channel. Okay, so I will advise that you subscribe to my YouTube channel to be able to have a notification whenever I post a video. Oh, thank you too. Thank you. So whenever I post my video, so I've already, this is also being recorded and this is also going to be published on my YouTube channel as well. I want to thank everyone once again for attending this lecture. It's extremely cold outside there. Make sure you dress warm in case you want to go out. Okay, gonna see you on Monday. Make sure you all stay safe and bye for now.
Thank you.
You're welcome.